Our next speaker is Dr. Jason Cassibry. Sorry about that. He has a BS in Aerospace Engineering from the University of Missouri, Master in Aerospace Engineering from the University of Illinois in Champaign-Urbana, and a PhD in Mechanical Engineering from the University of Alabama in Huntsville, which he worked there for a while as a research engineer in the Propulsion Research Laboratory over there. And after he received his PhD, he's a full research professor there. Thank you.
All right, thank you very much, and good afternoon, everyone. And with respect to the previous speaker, his piconewtons are still piconewtons greater than the propulsion that we've produced in our lab, but we're hoping to do something about that. So there are two main challenges in fusion propulsion. Well, there are a lot of them, but a couple of really big ones are, number one, we're fresh out of reactors that have demonstrated gain greater than unity. So that's the big challenge. But another one is, if you can actually do that, how do you take this isotropic explosion, if you're doing a pulse system, and redirect it in a useful direction to get thrust? So, but before we get to that, let's motivate why we're doing this. So for human piloted missions, if you stick with shooting gas out of a nozzle, you can compare these over here. Let's see which button. Yeah, there we go. So all these different curves represent different technologies like chemical. Then you have nuclear thermal, advanced nuclear electric, if you can get to 100 watts per kilogram. And then you have either pulse fusion and or fission or steady state diffusion. I think there was an earlier talk this week on that. But anyway, that pushes your round trip time to Mars down from a couple of years down to a few months. So it really does change the paradigm for accessing space with humans. Now, if you look a little bit farther out, here's a chart where we assumed an alpha of 1 kilowatt per kilogram for a spacecraft, basically the same spacecraft, and then took it to see how long it would take to do a sample return mission to all the outer planets and then some of the dwarf planets. So we take it all the way out to, I know that Sedna actually goes way out past Eris, but right now it's closer, so that's why it's over here instead of there. And so you're looking at some very significant distances here and trip times that are all less than 2 decades. So to go all the way out to something like Eris and come back, personally, I'd like to go to Haumea and see if the Mai Tais are better there than they are in Hawaii. But anyway, and just to make sure that we're not out of the realm of possibility, I did a quick calculation when we put these slides together to see what's the alpha on some other technologies that exist. So the diesel engine on a freight train, which has a 4 megawatt engine on it, is 23 watts per kilogram. The NERVA thermonuclear reactor has an alpha of 41 kilowatts per kilogram, and that had a 1.4 gigawatt jet power. The most recent example here, the Krusty nuclear electric reactor. I'm really glad that us Generation Xers get to name things now because we reference Simpsons and other things like that. There's an alpha of 6 watts per kilogram. So you can see that we're all kind of in the realm of possibility. And then the one in the middle there, the NERVA with 41 kilowatts per kilogram, is actually quite a bit higher than what we were assuming. And it's similar technology. You're dumping a lot of energy into a mass and throwing it out the nozzle. So we think we can get there with that. So, but as I mentioned, the problems for fusion are great. How do you get the temperature up high enough? Another problem is we're putting a lot of money into technologies that would result in very, very large systems. So ITER, which is being built in France, is comparable to Yankee Stadium. So we're not going to be putting that into orbit, so we have to look for smaller systems for spacecraft. And plus, if we use tritium, and admittedly in this talk, that's what I'm sticking with, deuterium-tritium, but if we use tritium and don't have onboard production of it, it's very expensive. Right now it's about $30 million per kilogram. So extremely expensive, you have to manufacture it. Just for those that aren't familiar with fusion, this is what it is. You take 2 light isotopes, something magic happens, and then out the other side, preserving the protons and neutrons, you get new isotopes and lots of kinetic energy for most reactions. And we're also interested in hybrids. We work with NASA Marshall and the PUF concept, which is developed by Rob Adams, involves fission as well. So what is fission? So you take a neutron, it gets absorbed into a really heavy isotope like U-235, and if it's a fast neutron, U-238 and thorium. And then out the other side, what do we get? So we usually get 2 or 3 neutrons and then a couple of fission fragments and lots of energy. It works out that both of those types of reactions, fission and fusion, have about the same energy per unit mass. It's like 10 to the 14 joules per kilogram. So compare that with chemical reactions, it's about 1 million to 10 million times more energy dense. So you can really think of nuclear as sort of helping us solve some of the storage problem. If you want lots of power for deep space missions, you can either transmit it there or you can carry it on board in that form of fuel. So it's a very promising technology for that reason. Now, specifically, in order to cut down that reactor size, we're looking at the magneto-inertial fusion parameter space. No time to really get into why, but it seems to solve a lot of the challenges and problems with mass and cost and size with some of the other concepts that are out there. That's not to say that it solves all of them, but it's very promising, so that's the area that we're pursuing. In terms of hybrid systems like that, which has been proposed by Rob Adams at NASA Marshall, you have this what we call a fusion power balance, where the axis down here is, think of it as the mass of the fuel, like a little quantity of fuel, times the radius. So it's the areal density, it's how big that target is, versus the temperature of that plasma. And so ICF, so the pellets that are driven on NIF, basically can ignite over in that parameter space. Now, if you add a liner in a magnetic field, you can push that parameter space over and use smaller targets because you're cutting down on the electron thermal conduction, which is really bad. Electrons are a pain. They want to radiate all the energy or they conduct it away. Radiation is really bad at these low temperatures, and then as you go up, the thermal conduction gets you as well. So magnetic fields help suppress a lot of that. Now, if you include a liner of even U-238, you don't have to have enriched uranium for this. The fast neutrons can actually burn with that surrounding liner and provide more energy. So there are a lot of promising ways that we think we can get the overall target mass and the yields down on these systems. So this is what we're pursuing, and this is the main machine that we are using to pursue these applications. This is Charger 1, located actually not too far from here on the Redstone Arsenal, over in the Aerophysics Research Laboratory. So this is the back end of the machine. It's got the capacitor banks in it now. There's Ross Cortez doing nothing but photo op, if I'm totally honest with you. This is an org chart. I'm a member of the Propulsion Research Center at the University of Alabama in Huntsville. There's lots of different groups supporting different applications in propulsion, and that's our little group over there as part of that. We have a consortium of a large number of agencies and those that have helped support this. So I just want to acknowledge that here. All right. So just to get you caught up on where we are with Charger 1, we just recently started firing the trigger system. It's a 3-stage system. And so they're now working on having that fire the second system, which would then fire the main bank. So we're actually getting really close. We've been working at this for about 5.5 years now to try to get this behemoth operational. A lot of little things that needed to be fixed. It was just sitting in a laboratory for 10 years unused, and we had to refurbish a lot. So we are looking at ZPinch based propulsion. And so the way that works is you drive a current through that central yellow conductor, and then the J cross B forces compress that down and hopefully ignite the plasma. There's a lot of challenges with that. We're aware of a lot of those. There are variations on that theme that we're looking at. The puff system, which I referred to earlier, involves basically some sort of combination of fusion and fission together. That picture at the bottom represents a notional nozzle that could be used where the plasma seen there burns and thermally expands and then blows out the nozzle. So you have these little pulses that come out the back. This is another concept that we're looking at. Mike LaPointe leads on this one. We need an acronym. If you have some ideas, we'd be glad to hear. I call it the LaPointe thruster, but he doesn't like it that I say that. Oh, whoops. That's just between us, though. So. But anyway, so the idea here is you drive a pellet through a magnetic field, and then that induces an azimuthal current on the surface and compresses it and ignites that. And you may need some preheating in order to get the temperature up enough too. But then it just pops out the other side and expands against the radial part of the magnetic nozzle or the magnetic field there. So today we're going to be talking about some simulations on the nozzle part. for fusion, because we wanted to try to, this year, start to address how to actually turn that into thrust. So one of my students a couple years ago did a master's thesis. He's sitting in the back corner over there, Kevin Schillo, looked at solid state nozzles for an ideal gas. So now we wanted to try, well, let's add radiation, thermal conduction, and finite resistivity and magnetic fields, and try to see if we can, capture some of these issues. The last time experimental magnetic nozzle work was done was around 2000, and at the end of that program, I heard one of the PIs on that program say the state of the art is that we barely know how to make a terrible magnetic nozzle. So there's a lot of challenges. So to meet one of those challenges, we're going to start with doing some simulations first to give us an idea of that parameter space. We use a code we call smooth particle, or SPF max smooth particle fluid with Maxwell equation solver, and it uses the SPH method for the fluids. So the idea here, I won't go through all of this math, it's just an interpolation scheme. It's still solving Navier-Stokes equations. It's just a convenient method if you have lots of finite chunks of mass and then lots of vacuum around it. It works really well because you don't need a lot of points in order to do a simulation. I can do full up 3D simulations on my laptop in just minutes or a few hours, sometimes a few days, depending on how sophisticated the simulation is. Here are the governing equations. I won't belabor that. It's just mass and then momentum and then electron and ion energy equations. It is a separate circuit model, which is self-consistent with that, and an electromagnetic field solver, which it actually has a couple of different ways in which we could solve for the field variables, one of which is to use the time rate of change of potential and vector potential and then derive the fields from that. We also do radiation matter interaction calculations, both multi-group radiation. We can do non-local reabsorption and stopping of the fast products, because you absolutely have to have those physics in if you're going to be able to do a good simulation for fusion. It's important to be able to do that. So we have that capability built in there. Just enjoy the pretty picture while I try to get this advanced. Yeah, if you can, just keep advancing until we get to the next slide. Thank you. All right, so this is sort of a notional vehicle design that we came up with back in 2010, which is derived from an earlier HOPE study. So this is for a crewed mission to Mars specifically. But just, so you know that we have a concept in mind for a vehicle, but let's go ahead and go to the next slide. And this is sort of an older picture of a magnetic nozzle. So just to try to illustrate, okay, we have a ZPinch in place, and then somehow the current has to return back through some flow path, and then the plasma is going to go through a nozzle. But we really didn't have an idea of how we're going to do this. And so this is sort of our way to try to address that. So the first thing that we did is just try several different types of nozzle geometries. So I gave names to the three that were kind of interesting here. So the first one we tried was, well, we don't really have a good idea of what to try. So let's start with the only advanced nozzle shape we know of, and that was the NERVA nozzle. So this is an actual 2-scale profile of the NERVA nozzle from the nuclear thermal program, with coil windings around it, and you see they cross because it winds up and then it comes back down the other way to help cancel the the off-axis component of the field. So turns out it didn't seem to work very well. We tried some very simple things like this ring geometry down here, and something that sort of looks like the bell on the end of a trumpet down here, and in all cases it didn't really work. We didn't get a lot of momentum transfer. So we were kind of befuddled by this until we started looking really at the field shapes and kind of realized that right off the bat there's really not a strong component in the right direction. You need J cross B force in the axial direction to get thrust. And so there's very weak radial fields with these geometries. And so we don't pretend to have thoroughly fleshed out this parameter space, but solenoidal fields seem like they just fundamentally had some challenges in order to try to produce the right field shapes. And we know that when the plasma expands, it does distort the field, but it didn't seem to really help it that much. So we came up with this other concept where the field coils actually sort of wind in a shape like this. So there's like a central column, and then they flare out and form sort of like this conical nozzle shape. And then I put an ablator plate in here to kind of keep the plasma from flowing backwards. And if you look at the magnetic field, it's almost zero right on axis, so it almost sort of forms a nice cavity that the plasma could flow through and get rejected from the very, very strong field that goes as you reach towards the surface. And so it turns out that actually worked pretty well. You can see the density on the surface there. It leaks backwards for a few particles because I used a very low density number density for the particles, and so it kind of seeped through, and that's easy to fix actually. But most of the plasma actually does expand and go up. This is one of the cases that we looked at, and you can see the little lines, the vectors, are where the current is getting induced on that surface to redirect the flow. So this actually started to kind of give us some results. Now, the code crashes right at this point, and that's something that we're trying to investigate. So we're going to have to run some test cases and find the little physics problems that are creeping up. But here's the ablator plate with no field, and here's with the field on. So for this case, we actually do get some benefit from having that magnetic field in. It's far from optimized, but now we have something that we can at least work with. In this particular case, we started with a 1 keV plasma. And it expands, and we can get only up to about 9,000 seconds. So there's some work to do, but let's say that we can figure out how to get this up to maybe more like 100,000 seconds and so on. What do you actually need for these deep space missions? So we looked at a gravitational lensing experiment. We assumed a 550 AU for that. And then we looked at Alpha Centauri, which is more like 269,000 AU, something like that. So this is sort of the mission analysis. To go to Alpha Centauri, it's going to take a long time. This is not optimized for that trip by any stretch, but it was about 260 years or so for this particular case that we looked at. If you pick something on here, if you go to the left, you can get shorter, but there's this exponential growth in the vehicle. But the gravitational lensing experiment is actually very interesting because you can get there in a matter of maybe a decade or so. So you can actually reach out to the lensing area fairly quickly. And so what we do here is just sort of flush out some of the performance parameters like mass flow rate of the fuel, the pulse frequency, if this is a pulse system, how often you have to fire it. And so for the gravitational lensing, I think it ended up being for the point on this curve we picked somewhere around a shot per second, which is not bad at all. And then for the Alpha Centauri mission, it was more like around 8 shots per second. So the burnout velocity, somebody just sneezed right back there, so it scared me. Okay, anyway. The burnout velocity for the interstellar precursor mission, as I would call it, is about 2% the speed of light. So it's nowhere near 10% the speed of light, and I think you could walk faster for the first AU or something. It's really slow to get out because the thrust isn't very high, so maybe we could put solar sails on the vehicle just to get it out of the solar system first to get it going. But there does seem to be some promise, and we have a path forward in order to try to get to these higher ISPs. This is just kind of a quick summary of some of the points that come out from the vehicles that would be needed to do these missions using fusion. And this is just some of the considerations and challenges. But since I think we're out of time, I'll go ahead and open the floor to any questions you have. And thank you.
My first question is, if you went with the uranium-238 liner, mm-hmm. what sort of changes to the facility would you have to have?
First off, we'd have to do a bit of radiation safety training, and there are a lot of issues with how you would handle that kind of stuff, because if you start burning products like that, there are laws in place that make that very restrictive. And so if we were to do that in the lab, there's a lot of paperwork that would have to be done, a lot of safety training that would have to be involved as well. So that's something that we're considering right now, just because it makes this a bit easier to do, actually, or it seems to.
What level of difficulty would it be if you used the liner as opposed to using pure fusion?
You mean if you tried to burn just the fission instead, like make it go critical?
I mean, well, use the fusion as a catalyst for the fission liner versus pure fusion.
Well, so we are actually working with NASA Marshall to kind of look at that spectrum from fission to fusion. And we think that fission is really important because it seems to help, but also they're kind of getting comfortable with using fission more. You've got like this crusty reactor. They're using like the radioisotope devices, and they're looking very seriously at doing nuclear thermal again. So they're working on that heavily. So they're getting more comfortable in handling that. And so we're trying to look at a spectrum to try to bridge from where they are to something more advanced to go out even faster. So. Can't really answer where on that curve we should be yet, but we're trying to look at all of it.